Hi everyone, my name is Lucia Perez. And throughout this presentation, my face is like, that picture of me is gonna stay in that corner. So if you're on Zoom, you can just like stick me up there and it won't block anything. I'm a final year PhD student at Arizona State University. My advisors for most of my PhD have been Sangeeta Malhotra and James Rhodes. But today I'm gonna be mostly talking about this work I did at the CCA as part of the pre-doctoral program. Where I created these new and larger simulations for machine learning alongside the CAMELS project. So for those of you who don't know, CAMELS stands for, it's like cosmology and astrophysics and machine learning simulations. So I created an entire new wing or hump of the simulations. And the two big questions, or like the big question that has been driving this project, is to think about what clustering summary statistics with galaxies is the best at constraining cosmology and or the baryonic physics of galaxy evolution. So the two big questions that I'll kind of guide us through in this talk is, with the clustering in the CAMELS-SAM volume that I've created, all these simulations, what is the best possible constraint we can get on cosmology just as a proof of concept? And then also kind of like dive into the clustering statistics and sort of see what they're capable of and how they compete with each other. So here's the structure of the talk. I'm going to introduce this suite of simulations to you. Then I'll kind of guide you through the galaxy clustering I've been doing and the neural network setup I've been using. Then we're going to dive into the best constraints we can get on cosmology and then on like baryonic physics. And then we're going to like compare all the clustering statistics and see how they do, and then kind of like wrap up and take questions or chat about things. Cool. So I really hope this video plays. So the CAMELS-SAM simulations, again, I told you a little bit about CAMELS. The original CAMELS suite is made up of about 4,000 total simulations. Half of those are n-body only, and then 2,000 are either through illustrious TNG or the SIMBA hydrodynamic models. But the original volumes are incredible. They're super good resolution, but they're only 25 co-moving megaparsecs per side. And that's kind of rough to do clustering with. So I created 1,000 new n-body simulations of 100 megaparsecs per side with 640 particles cubed. So that's about the resolution of TNG 300-2. And another thing that makes these simulations very interesting and like unique in what's available for machine learning training is that we have saved all 100 snapshots from Redshift 127 to 0. We ran full rockstar catalogs and all of the merger trees. All of that is stored for use. And then I ran all of these n-body simulations through the Santa Cruz semi-analytic model for galaxy formation to create sort of an analogous wing to the illustrious TNG and SIMBA simulations, but instead with the semi-analytic model. And another big thing that makes CAMELS very unique is that we have a truly outrageous parameter space for training. So in this case, our two cosmological parameters, omega m and sigma 8, cover very, very broad ranges around the fiducial values of 0.3 and 0.8. And that's because when you train machine learning, you want to have a very broad parameter space so you don't get really biased results at the edges of your field. I've practiced this talk a lot today, so I'm going to throw this a little try. And within the Santa Cruz SAM, we vary 3 different parameters that deal with supernova feedback and like mass outflow out of the galaxy, and also AGN feedback from the radio jet. And also an entire pipeline to do this. This was an enormous labor. I look back and I can't believe we managed all of this. And I'm really grateful to all the collaborators at the CCA that enabled this and the science that's going to come from it. Cool. And this is sort of one random simulation I pulled out. We can sort of see if you go through the whole volume, the beautiful large scale structure that we were able to form. And we're going to try to like get some summary statistics to be able to measure that in a way that makes it easy for a neural network to handle it. So let's talk galaxy clustering. This is my specialty. So in this initial thing, we're going to use 3 different statistics: the 2-point correlation function in real space, the count in cells distribution, which just says, okay, we drop a bunch of cells of a given size. How many galaxies are in every cell? Let's make a distribution. And then my baby, the Hoyt probability function that I will talk about later. And for this initial sort of proof of concept project, we're doing very simple selections: halo mass, stellar mass, star formation rate, that's it. We might also play around with like whether we downsample our galaxy clustering or not to control for number density. And we're going to stay with relatively like within 40 parsecs of like radii for our distance scales. So here, just to give you a sense of how the clustering looks in the volumes, I've plucked out 20 random simulations. I think this looks like 940 to 960. And I plotted them on top of a set of like cosmic variance simulations I ran, where I held all the parameters to fiducial, like realistic values, and then just let the random seed vary. So that's the gray area to give you a sense of the cosmic variance that comes with the volume of this scale. And then in colors, you see the clustering of all the different simulations. So the 2-point correlation function is a subtle boy, but it does show up. And count in cells really shows a lot. So to give you a sense of how this clustering should look like in your head to you. Cool. Now let's talk about neural networks. So I am new to neural networks and machine learning, and this project is a really beautiful introduction to it. And the real superstar for this, if you take anything away from this presentation, is the Optuna hyperparameter optimization package is incredible, because it helps you kind of figure out what the best neural network layout is. You don't need to go in and like change the layers you do, change how many neurons they have, what your learning rate is, just you put it in and it goes. So we have a very simple setup of 1 dimension to 1 dimension. I feed it all the clustering statistics in one long string and normalized. It gets all of the clustering in a row at 4 different redshifts. The neural network kind of does its thing, and it tells you the 5 parameters that should come out of it. And sort of basic things, this is a relatively simple setup. There's no more than 5 hidden layers. Most of them don't have more than like 600 or 700 neurons each. And part of the reason that the clustering statistics are really useful for this is because, you know, based on theory and like observations, we have a good sense of how clustering should respond to these different parameters. And also part of the reason we run 1,000 simulations, and even that number could be bigger, is because you need to have a really robust training set of 700 galaxies at least, or simulations, sorry, at least. And then 150 for validating each neural network to pick the best one, and then 150 at the end to test. So anytime I show you a plot of a neural network result, it'll have been for the best performing network given the testing set. Cool, so we've got a little bit of a sense of how the neural networks are run. Again, Optuna is amazing, please use it. All right, so again, the first thing we're gonna think about is, okay, I've run all these simulations for this enormous labor. What are the best possible constraints on those cosmological parameters that we can get? So we know dark matter only is like gold standard. How does that do? In this case, we do like an okay halo mass selection, like 2 times 10 to the 11 stellar masses. We downsample after the selection to 5,000 halos randomly. We measure all that clustering and we see what the neural network can do. And in this case, this is the best constraint you will see all day. It's beautiful around that 1-to-1 curve. I was really happy to see this. So kind of keep these numbers in your head. But in this case, the root mean squared error, I think we can take exactly as like an error on the measurement. So for example, if you were to give it hopefully like the real universe, it would say, oh, omega matter is about 0.27 plus or minus 0.013 from dark matter.
Just a quick question. For the correlation function and the, well, especially for the correlation function, what range of scales do you feed to the simulation?
Yeah, I go from about 1 to 40 co-moving megaparsecs because the 1 halo term was rough. I thought about this too. And that might be something I return to. But yeah, the 1 halo term I tried to exclude specifically because it got really noisy. And this is sort of a proof of concept. Like, let's keep things chill and easy, but thank you for asking that. Cool. All right, so we saw the best case dark matter only clustering constraint. How does galaxy clustering do? So in this case, we do a moderate stellar mass cut on the SAM galaxies, and we downsample to the same number density. And these are the constraints we get. This is the best I got of all the different things I tested for the SAM galaxies. So again, we stay about the same with sigma 8, which is quite interesting. And then omega matter gets a little worse, but it's still quite good. Cool. Now I'm gonna do a little experiment, which I thought was really interesting. And hopefully this will be interesting to those of you who aren't sure about neural networks. So here is the exercise. What happens if we train on a neural network on only dark matter clustering? We train it only on dark matter clustering, and then we give it galaxy clustering. So that's what I did in this exercise. So the green points are the ones you saw earlier. It was a neural network trained and tested just on dark matter only. And then the pink stars are what happens if you take that dark matter only network and you give it the stellar mass clustering. So clearly the constraints are worse if it had been trained on stellar mass clustering, but the information is still there. And the neural network is able to get a sort of broad sense of how the clustering underlying cosmology is. And this is essentially galaxy assembly bias. So this was really exciting. I thought this was cool. I hope you guys think this is cool too. But this is encouraging because even worst case scenario, if we have good dark matter only clustering measurements and we are thoughtful about it, then these neural networks will give a type of rough constraint on cosmology given real galaxies. So I thought this was cool. All right, now.
Was this in redshift space or just real space?
This is in real space. The redshift space would be a next step. And we can talk about that more at the end because I'm always thinking about, let's do this on like observed galaxies. How do we do this? How do we get there? But we can talk about it more. Thank you for asking.
Do you vary the galaxy formation parameters here?
Yeah.
But again, within some priors or?
Yeah, so the SAM parameters, we vary 3 of them. Here, let me see if I can find a slide that has it. These are the ones we vary. So these are varied, so like these are varied to be from 1/4 to 4 times their value. So for the ones that are amplitudes, they either get multiplied by 1/4 or up to 4 times, and like it's a log space between that. And then the slope in this law, I go from like plus or minus 2, that whole range is how it varies. So yeah, it's a little more complicated, but essentially like making it as small as possible and as big as possible. Does that help? It's a confusing way to explain it.
It was okay, yeah. Yeah, I got it, thanks.
Yeah, but we vary these 2 laws, so that does affect it. Cool, so, and something I will note, thank you for asking that actually, is that these cosmological constraints from the stellar mass clustering, these were done like on all 5 parameters at the same time. So these are the results, like I focused on cosmology, but the neural network was constraining all 5 at once. And something that's kind of interesting or promising is that if I tell the neural network to just focus in on omega matter, the constraints do not improve. So that means that the full neural network that's assessing all 5 parameters at once is seeing, it's getting at that core, like it's doing the best it already can. So that is encouraging too, that it's not like getting confused or like doing worse. And we'll see how sometimes focusing in can help. So now we can talk about, okay, the SAM parameters, right? Those were varied too. Can we constrain that? Do these actually have an effect? How do we tell them out? So in this case, we can take that same stellar mass clustering. We predict all 5 parameters at once. The supernova parameters do have an influence, but that AGN parameter is kind of eluding us a little bit. And also the bottom right is like all the loss functions of the top 10. That's sort of a helpful guide to make sure it trained enough. And if I remember correctly, I think the one that actually gets tested is the very first one, but don't worry about that. It's just a messy thing. And I had kind of a short time to compile all the plots. So we see that AGN parameter, and we know this affects the SAM. And again, this sort of controls the amount of AGN feedback from the radio mode. So maybe this stellar mass cut just isn't big enough, or we're not selecting the galaxies that would feel that specific aspect of their galaxy evolution. So we can instead try perhaps a 10 stellar mass cut.
Can I ask why is the neural network always giving some particular value for this parameter as opposed to a blob that doesn't, here, what sets that value that it's always choosing? Because
this straight line here. Yeah. That's the mean value of all of them. So it's finding the mean of all the distributions. Yeah, so in this case for the AGN parameter, it's 0.002. I don't remember, right? Because this is the amount that it gets multiplied by. So it's finding about like the mean value. So that's what that tells us, is that it's learning absolutely nothing. It can't make any predictions. There was this one weird little simulation that it thought it got something, but we don't know if we can trust it, right? So that's kind of how to read these plots. Thank you for asking. Yeah, you want it to be as close to the 1-to-1 as possible and like a really tight around it. And if you got a flat line, it's learning the mean that does the best. Good question. Cool. So we can try perhaps maybe like getting really, really high mass galaxies in the SAM parameter, and maybe we don't downsample, so we get the influence of number density too. So for example, like the supernova parameters really affect the number density after a given cut. Like they make way more star forming galaxies for us, like obviously. So we can get other, perhaps tighter constraints on the supernova parameters, but that AGN parameter, I've been chasing it for like a few weeks. And if I focus in on this one with this specific selection, it's still not any better. And I'm like, okay, fine, let's try star forming galaxies. And if we do star forming galaxies, then finally we can start finding a constraint on the AGN parameter. So that was really exciting. So we can get something pretty similar to the supernova parameters. And I will say that like nothing like this has ever been done with SAM galaxies. So I know every time I would show Rachel Somerville these plots, she would be like, oh, you should try this, or like, tell me about this. So to sort of give you a sense that like, again, the cosmology, we get really, really decently good constraints on because we're working off these merger trees of history. But the supernova parameters and the AGN parameter are specific to the SAM. So that is also interesting to be able to learn the relationships and inform how the SAM is run. Cool. How much time do I have left, Andrita?
5 minutes, I think.
5 minutes?
Yes, 5 minutes of talking, and then we have 5 minutes of discussion, if that's fine.
Okay, cool. So I will focus on like summary statistics and comparing the clustering statistics because I think it's really interesting. But I will say, my baby is the VPF. I've spent all of my PhD working on it. I really encourage you, if you can, like I have one paper that came out in January that studied the VPF as a whole. But the thing to know about it is that it's kind of a very simple clustering statistic that hides a lot of nuance and very interesting connections. So again, you're just asking how likely is a given circle to be empty if I drop it in my sample? It's the 0th moment of count in cells. It's tied to all the other higher order volume average correlation functions through hierarchical scaling. It ties back to like fundamental theoretical physics. And some samples can have identical correlation functions with different VPFs. So there was like, you know, the VPF has gone in and out of fashion a lot. I'm trying to bring it back in fashion. So I have one paper that came out in January that sort of like, I think taught me how to measure clustering in like an intelligent and thoughtful, careful way on samples of a few thousand galaxies. Because, you know, sometimes if you're doing Lyman alpha emitters, you're lucky if you get 100 or 200 in your sample, you know. And I also have one paper that will be out probably on arXiv next week, constraining reionization for a narrowband survey with the VPF and kind of making predictions for that on another simulation. And a paper that I'm working very, very hard on to see what kind of constraints on reionization Roman Space Telescope will give if you use the VPF of Lyman alpha emitters. And the reason that one is cool, I'll be really quick, is that with the VPF and these simulations I've been working with, you know, I can tell the Roman people, if you have this specific limiting depth, say a deep field that goes to 10 to the negative 17 ergs per second, you can be okay with 4 or 5 square degrees, which is great because some folks who have been doing papers, for example, the angular correlation function with like the 21 centimeter constraint, that takes 20 square degrees. That's really hard. So maybe the VPF, again, if you're not thinking about, if you're just kind of treating it at face value and you're careful with how you handle the errors, you can make some constraints with less area. So that's really helpful. So please ask me about that later, or keep an eye out on the arXiv for it. But back to CAMELS, right? So we're going to compare all these 3 clustering statistics I've been working with. to kind of see where their strengths are and where they're contributing. So again, here we are, dark matter only clustering. And in this case, the GIF is not working, which is really upsetting. Does it do it? It does, or it doesn't. Okay, so I had it like sliding through all the different constraints, but I wrote it down on the table for this reason. So one thing we'll see as we run through all the different clusterings, a very interesting pattern emerges, which is that the VPF tends to do quite well at getting omega matter. It tends to dominate the constraint and do the best job at it. And the 2-point correlation function in count in cells ends up doing quite well at sigma 8. So I think that's really interesting. And when we look at the baryonic constraints, the VPF ends up kind of being the one that dominates and helps constrain it the best. I think this is very obvious. Again, like the GIF is kind of a bummer, but it's okay. And this is kind of interesting. I know my advisor, Shai and I have been talking a lot about it. And I think part of the reason why this happens is because the VPF, again, is the 0th moment of count in cells. It tends to be sensitive to number density. And it really, it's tracing voids, right, in a very statistical sense. I don't know, I need to think about this more and chew on it. If you're interested in this, please talk to me about it. But this is a very interesting thing. So I think my takeaway, my second one from this talk, is to not discount the VPF. It's really easy to measure. And if you're just using it as a statistical tool to constrain things, it can do quite well. Okay, so this is my last slide. Again, I ran all these new simulations to make a new hump for CAMELS. It consists of 1,000 n-body only volumes of 100 megaparsecs and 640 particles per side. We have all the snapshots, rock star, consistent tree, all of the halo information saved on the Flatiron clusters. And each has been run through a unique iteration of the Santa Cruz SAM. And I've shown you today that we can use galaxy clustering to get good constraints on cosmology with SAM galaxy clustering. And I have a bunch of ideas of where I could take this. There's my email if you're curious, my website that's in progress of being updated with other projects. But thank you so much for your time and for listening. This work is really great, and I've worked with some Princeton folks, so I'd love to hear more from other people.
Thank you so much, Lucia, for a wonderful talk. And thank you so much for staying perfectly on time. Are there any questions for Lucia? Again, I can't see, so please just jump in.
I have a quick question. What kind of likelihood did you assume for this VPF and counts as cells PDF? Did you assume the Gaussian likelihood for all of them?
What do you mean, what did I assume?
When you were doing these feeds, for instance, showing the constraints on sigma 8.
Oh, okay. Okay.
Can I think of this as doing some Gaussian likelihood, or it's everything machine learning, so you never compared with?
No, I never compare to anything. Yeah, that could be something to add in, is the expected clustering given the number density of the samples. But in this case, it's the neural network, all it gets is the values of the clustering measurement. The VPF, all of these I measure with CoreFunc, the package, it does it well. But yeah, it's just the neural network kind of doing its inner hidden magic to figure out, the mathematical relationships that would get out the parameters we want. And I know something that would be, I think other folks have done it, is using or confirming, I guess, theoretical relationships between clustering and theory with neural networks. But yeah, there's no Gaussian processes here. It's just the neural network doing a very simple, either mean squared error loss function, or Pylian's, Baco has developed a loss function inference function. That one I implemented pretty recently, and none of the plots are they're all kind of ugly right now, so I don't want to show them. But both those are all consistent together. They're giving very similar types of constraints and errors. Does that help?
Yep, thanks.
I have a question. Am I correct in understanding that you gave it 4 redshift splices at the same time? You imagine a combined survey that include all of those. Have you explored whether where the weight comes as a function of redshift, or if one redshift is more important than the other, or is it the differential between redshifts, or what?
Yeah, it's a great question, and I actually cut that from the talk for time. So it's not super conclusive yet. Like doing it by individual redshift does a little bit worse, but not in a super clear way. Like most of them, redshift 0 tends to do the best, and I would imagine that's just because we have like a longer merger tree history and like more objects than naively. But they tend to be pretty similar between redshifts. Yeah, so that was one thing where I kind of like helped myself out. I think like the scale of those constraints, I'm not sure I can pull it up like quickly, but they were a little worse. But yeah, this was definitely like helping it along. Yeah, good question.
And so you were saying earlier that you'd like to extend this to redshift space, and then eventually would you like to apply this to which sort of data would you like to, what's your vision for the future?
This is like my postdoc proposals right now, essentially. There's a lot of work. Oh, I have so many ideas. Yeah, so there's making the clustering clearly like more reflective of what true galaxies are like. I know one path that I would be interested in taking just due to my experience in grad school is comparing to narrowband clustering. So emission line galaxies, for example, with like narrowband surveys like Logger or others can get, you know, really, really narrow redshift slices. So apart from contamination fractions, like, you know, those are basically where you expect them to be. So the two-dimensional clustering is a little simpler to handle with that. And I've done that before. I've done it on observed emission line galaxies. So that might be the path I might like wander down first, just because it's a little more familiar. But I know there's been a lot of folks who have done different things. So for example, Boriana Hajiska from Harvard showed that you can do like specific types of cut on illustrious galaxies to get and like make a good daisy emission line galaxy sort of mock catalog that like matches the big summary statistics relatively well. The other thing that is important is like these do not have photometric there's no photometry on these galaxies, and that is a very significant computational investment that we have to seriously consider if it's worth doing. Because these simulations, like in total, like the snapshots alone are over 500 terabytes after being compressed. The consistent trees are like 60 terabytes, so I'm not sure how feasible it would be to do that, but that would be the dream, to get like photometry, spectral energy distributions, and like get emission line luminosities. But I don't know, I'm thinking about it. It's definitely stuff I'm thinking about.
Thank you.
Thank you very much again, Lucia. I think I would say in the interest of time, let us move on to our second speaker. So
Yes, thank you again. Sorry.
and you're very welcome to stay, Lucia. But if you need to go somewhere, that's also totally fine. Taylor, would you be up to sharing your screen? Great, thank you so much. So please take it away. Thank you so much for making it today.
Thanks. Hi, everyone. My name is Taylor Hoyt. I'm a graduate student at the University of Chicago. I'm currently applying for postdocs. And I'll be giving a talk on a couple of recent results that I've put out and been a part of on calibrating the tip-the-red giant branch method and how that impacts measurements of the Hubble constant. So quickly, I want to go over the cosmological stakes, because that's what really matters to you all here and really matters to the universe. So I'm showing two plots from a review from Di Valentino et al. And on the left are basically proposed relaxations of the Hubble tension by invoking early dark energy, which is basically the conjecture of a different substance, dark energy like substance before reionization, and that basically changes the size of the sound horizon to resolve the Hubble tension. On the right, I'm showing a plot from the same review for late dark energy solutions, and that would be, if I understand correctly, I mean, I'm sure there's a big model space, but basically it'd be phase transitions at late time dark energy. So deviations from, WA basically is how I categorize that, but I'm very open to being my understanding broadened by this expert audience. And so also shown are bands that show the H0 measured from the Cepheid-supernovae distance ladder and also inferred from the Planck-based lambda CDM. And what you can see, basically, I'm showing these to show it's kind of hard, as you all know, to make it all the way from base lambda CDM and Planck to the Cepheids. And what I see this as, there's almost some argument for perhaps it shouldn't be so hard. And oh, it's not letting me progress my slides. Oh, there, phew. So now what I'm showing here is our new measurement of the Hubble constant using the TRGB, calibrating the supernovae 1A in the Hubble diagram. And I think this red band on the left got shifted. It should be directly in between like the one on the right. But essentially what I'm showing here is that the precise value of the Hubble constant matters. And I really think that discussion of the Hubble tension needs to evolve from, say, X, Y, Z, sigma detection of new physics to what is the accurate value of the Hubble constant, and how does that constrain the model space? Because we don't want to send theorists who are working very hard to resolve the tension chasing down rabbit holes that aren't actually tethered to reality. So we really want to focus on an accurate measurement wherever that may land, because of course in the limit of infinite precision, tensions will always arise. We want to make sure that our uncertainties reflect reality. So as you could see from the comparison of the Cepheid and TRGB H0, there is a tension within the tension, which I refer to as the Cepheid-TRGB discrepancy, distance discrepancy. And essentially what I'm showing here on the right is a comparison of Cepheid and TRGB distances to 10 supernova 1A host galaxies, which are the crucial anchors of the supernova 1A Hubble diagram and thus the Hubble constant. And so the difference is about 3% in distance, which comes out to be exactly the same amount in H0. So of course the TRGB, we find H0 of about 70, and the Cepheids find about 73.5. And recently, to resolve this discrepancy in empirical distances, there's been a lot of focus on recalibrating the CCHP measurement or calibration of the TRGB. However, you may have seen recently in a review from Wendy Friedman that was argued that with a larger number of calibrations, the issue can't be in the calibration. I've also dedicated my own recent efforts to nailing down this calibration in a couple of recent papers, which I will run through here.
Can I ask a question? If we go back to this plot, sure, there you can make a line and say 3% or whatever, but from here I can see that my takeaway would be that the plots are scattered by a lot, and those error bars are off, because
precisely
so off. I mean,
precisely. So the scatter is about 8% in distance, but the typical uncertainty is about 3.5%. So the error bars are underestimated by about a factor of 2, which is terrible. And that is, I'm really glad you asked that question. That is the exact takeaway from that plot, that the error bars are underestimated.
But why don't, I mean, okay, so we just put these error bars that you measured from here in some sense. What would that mean for or is that how you propagate the errors, or are you still using the errors that are implicit in those points? When you call
that's the rest of his talk, is answering that question.
I don't fully understand the question. So
When you will quote your final answer for the Hubble content,
yes,
are you based on the errors that are being propagated? Are they based on what I can see from the scatter, or
yes, they are. Yes, they are based on the quoted uncertainties. And so that's my point. So this whole talk's gonna be based on, getting to a point where we need to look for systematic errors. So you jumped to the answer, which I'll talk about right now. So basically, both the CCHP and SHOES, the team led by Adam Reese doing the Cepheids, have basically found that the offset, the difference between the Cepheids and the TRGB can't be due, I'm going to speed up a little, so excuse me, can't be due to the supernovae. And so can it be in the supernova 1A calibration? That would be the distances I just showed. Possibly, and also could it be in the calibration of the methods? Possibly, and that's what's been focused on recently by the SHOES team specifically in a number of papers, recalibrating our measurements. And that's what I'll be talking about in this talk and kind of settling for good. So the context here is really, I don't want to get through all this text, but basically you can see in this plot that basically just plots up the proposed calibrations of the TRGB distance scale. It's in the magnitude system, I apologize, but I've included little translations to H0 so you can get a sense for how this affects the final H0 measurement. And on the left, the arrows point to CCHP calibrations, which of course line up with H0 of 70. On the right, you can see proposed calibrations from the SHOES team, which all conveniently line up at the answer that gives you the Cepheid result. So I really wanted to avoid what is clearly turning into a modern version of the factor of 2 debate. And I wanted to write my own paper on TRGB calibration that just ignored the cosmology and looked at the astrophysics to get the best calibration of the TRGB that's possible with the data available today. So before I get into that, I want to train everyone's eye into the idea of what an accurate TRGB distance is. So essentially they can be precise, TRGB distance can be precise to as good as 2% in distance if done correctly. So basically you have to find, I'm gonna run through this too, low mass, metal poor, red giant branch stars with negligible or quantifiable extinction along their lines of sight. And old is a proxy for age in our universe, of course. And so how that manifests in empirical measurements, as you can see here from a sample of dwarf galaxies, the TRGB is this clear discontinuity as stars climb the red giant branch, and they trigger helium burning in their degenerate cores, and they very quickly ignite helium burning, they run away, but then degeneracy is lifted because they're at this threshold basically where the ions can gain enough energy, relax the degeneracy, and then it becomes an ideal gas. And then they quickly evolve off of the tip of the red giant branch into the horizontal branch or red clump, which are about, an order of magnitude, 2 orders of magnitude fainter on the HR diagram. And it just so happens that for those criteria I outlined, the luminosity at which this helium flash occurs is the same. And that's the standard candle basis of the tip of the red giant branch. And so here are similar examples of good TRGB detections in the halos of L-star galaxies, which is what made up the CCHP program. And on the left, you can see our targeting of the halos of the supernova host galaxies. And on the right, the color magnitude diagrams and TRGB measurements. There's more scatter and they're not as deep because these are more distant. Photometric errors are larger. So how does this apply to calibrating the TRGB? So I'm going to turn to the Magellanic clouds, which is where much of the debate has emerged over the TRGB calibration. So that was me showing it relative to the galactic plane, the Magellanic clouds. And here are the Magellanic clouds again, with the moon plotted for size, just to get an idea for the scale of the data sets needed to measure the TRGB or anything in these galaxies. So the important part, why calibrate in the clouds? So they are these abnormally old and chemically deficient dwarf galaxies, dwarf satellites of the Milky Way. And a plot that really nicely summarizes this is from a recent paper from Nidover et al. Using apogee. where basically a spectroscopic tracer of star formation is particularly depleted in the Magellanic clouds, as you can see here. I hope you can see my cursor, with respect to the total integrated stellar mass in these galaxies. And so, as I mentioned, old and metal poor is how you get TRGB stars that are standard candles. And so the Magellanic clouds are actually these freaks of nature in the universe that are almost designed for measuring the tip of the red giant branch. And so that's why it's really important that we can do the best that we can possibly do for these galaxies. And so what is essential for measuring the TRGB in the LMC? So first, this is the one that's received a lot of traction of late, and that's corrections for line of sight dust extinction. For reasons I can get into with questions, a recent paper from the OGLE collaboration presents the most definitive you can possibly get. It's a really incredible paper, Skoran et al. And that it really settled the idea of dust extinction in the Magellanic clouds, in my opinion, at least to the fields that will calibrate the TRGB, and that's for specific reasons of their probes. So basically the probes they use to measure the extinction to the Magellanic clouds are actually, TRGB stars are actually the progenitors of the stars they used to measure. So it's perfect for the TRGB. Anyways, you also need a geometric distance, which we get through detached eclipsing binaries, Petrinsky et al. 2019, if you've seen it. And then we have to actually correct for the three-dimensional tilt of the Magellanic clouds with respect to the sky. And that is about a 2% effect in the region that I considered, at least in my recent paper. And so the remaining piece that I decided to fill in my latest paper was an accurate determination of the mean TRGB magnitude to the LMC. And what's crazy is basically in this galaxy where it should be perfect, it's the perfect environment to measure the TRGB. There's a dispute at 0.08 magnitudes, which is about 4% in distance, which, as you know, as I discussed, is about twice as large as the total scatter when you consider the TRGB as a standard candle. So we have to be able to do better. And so to do that, I broke up the Large Magellanic Cloud into individual fields and classified each field by the perceived quality of its Hertz on the Hertzsprung-Russell diagram, which is just stellar luminosity versus temperature. Basically where the best case resembles those good detections I showed at the beginning. And it turns out that after I do that qualitative classification, quantitatively, through a bootstrapping procedure, you could see that the low ranking regions oversample these imprecise and broad false peaks, false edges when sampling across the full LMC. And that's shown here on the left, where the black
Which
yes.
data? You said the quality of the HR diagram. Where are you getting the data for the HR diagram from?
Yeah, so the OGLE survey releases, yeah. So you can see the black outline on the right is the footprint of OGLE 3. And that's the publicly available photometry I use to construct the color magnitude diagrams. I can show examples, but I left them out for the sake of details, and I can show them. So the black distribution is if I uniformly sample random stars across the whole face of the LMC, which I deem that control. So that's if you pick any random locations across the Large Magellanic Cloud, what do you get for the TRGB magnitude? And then separated into blue and red are the highly ranked fields and the low ranked fields. And so the highly ranked field you can see is singly peaked. While the lower ranked fields seem to have multiple peaks that are much broader and all over the place. And basically that the TRGB is a standard candle. So if you can't have multiple TRGBs in one galaxy, it's impossible. So that in itself already tells you that those fields can't be used to measure the TRGB because there exist multiple. And furthermore, when you do the quality control that I did with the color magnitude diagrams, the it actually just amplifies what's already the dominant peak in the control sample here. So you can see that this black peak here is the dominant peak in the control sample. And when you select for good TRGB quality fields, that just amplifies that dominant peak. And on the right, you can see that the red are the bad fields and the blue are the good. And the red is found to trace basically star-forming structure in the Large Magellanic Cloud. So basically the darker regions on here have higher dust extinction. And the white dots here are the calibrating detached eclipsing binaries, which are very young populations. And so it's a good tracer of very young populations, less than a gigayear, a few hundred megayears in age. And the TRGB has to be measured in ages about older than 4 gigayears. So there is physical basis to this.
Sorry, can I ask, why would this plot on the left have peaks as opposed to, like, why are there some missing values there? Why is not, yeah. How do I understand why there are many fields with one value and nothing in between? Seems like there's some discontinued choices.
So the peaks you're seeing are, so I should have explained this more clearly. So drawing from the total Hertzsprung-Russell diagram of all of the blue regions, I bootstrap subsample, I think it was about 70%, and I measure the TRGB magnitude. And I repeat that some thousands of times until it converges. And so that's what builds up this distribution of TRGB magnitude frequency that you see on the left. Sorry for rushing through that. So these are realizations. So each block here, you can't see each rectangle in the histogram, but each one is a bootstrap realization of the samples you see on the right. Does that answer your question? So basically,
I was just wondering why, for example, there is such a small amount of fields around 14.5 and then goes up again. Like, is this to do with the structures of the dust? And then there's long correlations of regions that have one value of extinction. Yeah, I just don't understand why the structure of these peaks.
So why, yeah. So it's hard to answer why there are these false peaks. It's hard to expect a smooth flat distribution, but what I think, at least this secondary peak here, I think there's actually variations in the extinction law that are causing the translation from the color measurements of this probe from the Ogle survey and mapping that into an absolute extinction. So I really think it's variations in RV, and I think that's mostly why it traces star forming regions. But I can't really show that, but I have some ideas for doing it. But to be honest, sometimes it's better to just throw out in terms of the absolute distance scale. And so just to show an example, so this is what maybe I should have shown this first. So on the left are the combined, so the top left is the full Hertzsprung-Russell diagram from the blue regions you saw on the previous slide, and the bottom left is the full HR diagram for the red regions. So you can see as there's, that really clear truncation of RGB stars. And this is the basically our first derivative of the smooth luminosity function selected within this color selection, which was designed to isolate a flat TRGB feature. So you can see that the selection really does, the classification scheme, the ranking I did really does converge on these kind of best case scenarios of the TRGB, while the bad regions are kind of this blur where you can't really make out an actual feature. But here you can actually you'd even accurately determine the TRGB by eye. And it's really, it's the highest precision measurement of the apparent magnitude in the Large Magellanic Cloud to date. And it's really kind of self-evident in my opinion. So I think I'm running out of time. So just very quickly, so a lot of these, so the problem is a lot of the previous calibrations in the LMC used these lower ranked regions, which you can see here. So this might answer your question for the source of these other peaks. were the fields adopted by these authors, and these authors actually have a bimodality in the TRGB magnitudes, and then they averaged over that bimodality, which of course gives you that splits the difference between the two modes. And so that was what was leading to this bias in the TRGB measurements, because they had some good fields and some bad ones, and they're averaging them. And what happens if you combine the measurements, you can actually, just through a signal processing argument, you actually can alleviate some of those biases rather than breaking it up and averaging. Because of course, averaging biased with unbiased gives you half biased. And so there's a number of consistency checks I did that I'm not going to get into, but they're, basically they reflect that we really fully understand the true distance, reddening, and the multi-wavelength TRGB magnitude color relation across the Magellanic system to better than 2% in total accuracy. Otherwise, all of these kind of nodes that I checked would have fallen apart. And I can get into that more if you're interested, but I want to really move on because I bet I'm running out of time. So another galaxy is NGC 4258, where the masers orbiting supermassive black hole, their orbital motions can be modeled and a trigonometric distance extracted from their radial velocities and proper motions. And so what I'm showing here are 3 recent calibrations of the TRGB in NGC 4258. One from Reed et al. 2019, one from Zhang, Hoyt, and Beaton et al. 2021, and one very recent one from Anand et al. 2021. And so just note, this is the location of each of them. And I'm not going to get into it too much, the other ones, but I will talk about the very most recent result in Anand 21. So their measurement, they claim it's in the halo and it's a good TRGB measurement, but as you can see on my plot on the right, it's very much still at least partially in the disk of this galaxy. And most importantly, one of their fields is hit right by this kind of plume of H1 gas, which is undoubtedly biasing their result. It's also lower signal to noise than the prior data set used by the Cosmic Flows group, which was weird. And yeah, so I'm not sure that that's really the best measurement, even though they claim it is. On the other hand, that same paper did corroborate all of the CCHP's distances to the supernova host galaxies with a total cumulative scatter of 2.5%, which is just resounding. So you can see that here in the top right plot, where the offset between the two groups' measurements is 0.001 magnitudes, which is 1/500th% in distance. And then in their recent paper, that only deviated because they changed their calibration. So they had this calibration, RITSI 2007, that they've used for 14 years, but they decided to throw out with this lower quality data, which was odd. And so that shifted their H naught from ours by about, I think, 1.5. And so anyway, circumventing all of this, the final say will come with new, better HST data. So in the recently approved HST program, I was given time to sample the true halo of NGC 4258 at the highest signal to noise ever measured, 2.5 times higher than all these prior measurements. In the halo, I specifically avoided all H1 emission, and the quality data set will be so high, I'm certain it'll reach the systematic floor set by the distance and the foreground extinction. And as a bonus, it'll give the first direct calibration of the TRGB and infrared filters on board the Hubble Space Telescope. And you can see the locations, the planned locations on the right, where they tightly hug the kind of boundary of the halo that we found in this prior paper, marked by the white circle. You can see how they're exterior to the previous calibrations that were in the disk. So if systematics aren't in the CCHP TRGB calibration, then where? Hopefully I've convinced you that the TRGB calibration is just fine. So if it's not there, then where could they be? So Cepheid source crowding is really the outstanding issue that still hasn't really been answered to any satisfying degree. Here is in the anchor galaxy EGC 4258, and on the right is one of their Cepheids, one of the brightest Cepheids in their whole sample, shown in optical wavelengths on the left of this kind of quad panel figure. So the left column is optical, and it's the same star just zoomed in. So the bottom row is just a zoomed version of the top row, and on the right is in the infrared. And so that's the real problem. So the SHOES team moved to the infrared to reduce systematics due to dust and metallicity, because both are mitigated there. But it may turn out that they've introduced a bigger problem, and that's source crowding, or blends, as you may have heard them in the context of LARC, that's the cosmological data sets. So the scatter and the Cepheid period luminosity relation is supposed to decrease in the infrared, but the opposite occurs in their sample due to crowding effects. So you can see on the left in the optical, the scatter is about 0.16 magnitudes, which is about 7% in distance. And on the right is the infrared version of the same Cepheids, where the scatter is now about 20% in distance. And that's in a calibrating galaxy. So it's, and this is also only showing sigma clipped Cepheids. So they clip at 2.7 sigma. So you don't even see the wings of how bad it is out there. So it's unclear what has really been clipped and whether that could be, biasing, if it's asymmetric, you can't sigma clip, but we don't know if it is or not, that distribution. So we really need a fully independent re-reduction of the SHOES data set, which has not been done yet. It's been done for one galaxy out of the 19, but not for the full 19 galaxy sample. And just to point out, the SHOES team also agrees that this is a problem, as evidenced by their recent proposal with James Webb on uncrowding the Cepheids to improve determination of the Hubble constant. So that gives you an idea that this really is a serious issue. And just for comparison, these are our measurements of our RGB stars in the halos of galaxies. This isn't an issue for us. So what we can actually do is dig deeper into problems like photometric calibration and PSF modeling, because we don't have to worry about the really baseline issue of 300% of the flux of a Cepheid coming from a neighbor star.
1 minute.
Okay, thank you. This is my last slide. So with the new HST calibration that I presented here, that will come in the next year, we'll get to a 1% calibration of the TRGB. And hopefully, if as we move into the infrared, which I won't get into now, but in about 5 years, we'll be able to reduce the uncertainty and the biggest error term remaining in H0 measurements significantly, because the TRGB is basically 6 times brighter in the infrared and will let us probe much further in volume, at least tenfold increase in volume. And so that would bring the total to about 1%, optimistically, obviously, but I think it's actually very possible. So I'm going to skip that and go to takeaways. So it's not possible for the TRGB calibration to be off by more than 0.02 magnitudes or 1% in H0. Thus, the divergence between Cepheid and TRGB H0 must be in the measurements to the distant supernova host galaxies, which are the most difficult measurements to make for both methods. So it's important that we really get over, I really feel strongly this, but we get over bickering and falsehoods in the literature to support or be against a certain cosmological outcome, and really get into the astrophysics and what's really going on here. Because, for example, in the 1990s, the factor 2 debate wasn't actually solved by just new physics. It's actually resolved by both the new physics in terms of dark energy and the identification of systematics in prior H0 measurements. So it's very likely we'll see the same resolution here with a combination of extensions to LCDM and resolution of systematics. Yeah, and that's all.
Thank you very much for a very nice talk. I think I'm gonna echo, so first of all, thank you so much for staying on time. And I think I'm gonna echo your last slide, because we're basically at the hour and we've had several questions already. So I think if you have more questions for Taylor, please email him or contact him in any other way. And I think with that, I would say let's close for Cosmology Lunch for today. Thank you both so much for 2 very nice talks and for staying on time. And for all of the others, see you next week.
Thank you.
Thank you.
Thank you. Thank you for having me. Sorry for going right to the limit.
Can I ask a question anyway? You're still in Zoom and people can leave. Are you there? Yeah.
I'm here. If you're talking to me, yes, I'm here.
Yes. Can I ask you? So, I mean, this issue of crowding has been brought up many times. As far as I mean, I'm an outsider, right? But there's supposed to be a term in the error bar of the shoes that includes these, and they were doing, you know, simulations in which they took a fake galaxy and moved it back and did some blah blah. I don't know. That's what this guy is always telling me when I ask him.
No, so that would actually be an ideal measurement. So what they actually do is they inject a Cepheid. So if you look here, so you know, they basically make a cutout and they inject fake Cepheids into this image, and they measure basically the potential bias due to the fake Cepheids location in this local scene. And the problem there is that they enforce that their measurements are at least 2.5 pixels away from all measured sources. And the problem there is that actually completely negates the ability to test for blending, right? So
they don't put Cepheids anywhere at random. They put them, they avoid putting them on top of another one or something like that.
Exactly, yeah.
Oh, but that's, are you sure? Is this true? This looks
yes.
like...
Yeah, so they're actually, I think they're more looking for variations in the sky background and how a gradient in the sky might bias their measurements. They don't actually assess blending. And so their argument for reducing blending is they make a color cut. And so basically they argue that if an asymptotic giant branch star, which are these stars that are suddenly revealed on the right, they're dust enshrouded, very red. And when you go to the infrared, they become extremely bright. And so that's what's swamping the Cepheid here in the infrared. And their argument is if flux from an AGB star is contaminating your Cepheid flux, the color, the photometric color would be significantly biased to redder versions. So they make a color cut. I don't know the exact value, but they argue that that gets rid of all possible blends. And I bet it mitigates it a lot, but the colors just aren't precise enough that there's going to be so much contamination still. So, but I mean, it could still work maybe in the average, but it's just hard to say because they don't provide that data. They only provide the clip data set.
Yeah, this issue of clipping is also very
yeah. So that's my main motivation for wanting to re-reduce the whole thing. At the same time, you know, if I get the go ahead to do that, e.g., it's in my postdoc proposal, I would make, you know, everything public before clipping, and also, you know, all the code, the analysis tools, the key data, because it's very obfuscated right now. And, you know, I don't know, I haven't worked with the data set enough to really know if there could be something super problematic going on, but it's still, you know, restrictive to the field in general to not provide all that, because, you know, there could be interesting physics just in there missing, even if H0 doesn't change.
But this would be a very good service to the community and the field, and I hope you will get recognized for it as opposed to destroyed. I don't know, I guess, right? It's very political, this whole thing.
Yeah.
Yeah. I mean, not for me, but...
Yeah, it can be a bit overwhelming with how political it is. It's yeah, scary at times.
Yeah. Well, thank you very much.
Thank you for having me.
Good job, Taylor. I wanted to tell you in person.
Oh,
Send me
hey, Rachel.
I'll tell you in Slack
Thanks.
too, but okay.
Bye.
Bye.
Or hey.